All right, let's take a moment now and talk about RL circuits. So imagine I have a battery that is connected in series to a resistor and an inductor. So VAB in this case would equal IR, and VBC would equal L delta I over delta T. So I can use Kirchhoff's laws here, and I can say that the EMF across battery minus IR minus L di dt is equal to 0. And for solving for delta I over delta T, gives me some information about what the current looks like at different times. So initially when T equals 0, well, I is effectively 0. So that means that my current I is going to look like EMF over L. When T is infinity, well, then my delta I over delta T goes away. So when I close this circuit, originally delta I over delta T is very large, so the vast majority of the potential drop is going to be across the inductor. At infinity, I'll be at a steady state condition, which means that delta I over delta T is effectively 0. And that tells me that I should look like EMF over R, and I can get that by solving this equation when delta I over delta T is equal to 0. So that tells me that 0 equals EMF over L minus R over Li. My L's cancel, and I end up with I equals EMF over R, which is what I would expect from Ohm's law. So when I think about how the current varies as a function of time, that's going to look like this. So I as a function of t is going to look like EMF over R times 1 minus e to the minus R over LT. So when t is equal to 0, I have no current. When I flip that switch initially, my current starts looking like, what did we say, EMF over L. And when t goes to infinity, this term goes to 0, and I'm just left with, let's see, this term goes to 0, and I'm just left with EMF over R, because this exponentially decays. So that's what my current looks like. I can also say that the energy dissipated, or the power dissipated, is going to have two different pieces. So one's going to look like I squared R, and one's going to look like Li delta I over delta T. So initially, the power is going to be dissipated across the inductor, and over a long time frame, it's going to be dissipated over the resistor. We could also solve this using calculus, but I think just looking at these two conditions and saying that it's got to exponentially decay between the two is sort of the easiest way to understand it. And we also have a time constant in this case also, and the time constant is R over L. All right. We can now talk about RC circuits, or sorry, RCL circuits, or LC. And here I have some Q max and some Q min with some EMF, and then I can discharge the capacitor through an inductor. And if I think about that, the V here, right, or the potential difference is equal to Q over C. And here, the EMF is in the opposite direction, right? So initially when I discharge this, I'm going to have a lot of current coming through this direction, which means I'm going to induce an EMF here in this direction. And then it's going to start slowing down, which is going to induce an EMF in the other direction. And that's going to give me sort of an oscillatory effect, so I might have a frequency I can relate to. And I also end up with this relationship now that these EMFs are sort of all in very different variables. But I can think of the potential drop across the circuit as being 1 over CQ, and the other as being L in the opposite direction, change in Q, change in time. And if you know anything about calculus and you've looked at differential equations at all, these kinds of relationships, this one has a minus and this one having a plus, gives me answers that look like sines and cosine. And that goes with this idea that I'm going to have this oscillatory behavior, which we see just in the ramping up of I, changing the EMF direction where it initially increases and then starts to decrease. And I can define an omega, which is a frequency, which is equal to the square root of 1 over LR. And, LC, sorry. And if I take this a step farther, I end up getting something that looks like d squared q dt squared equals 1 over LC q. And here q is a function of t with a minus sign. And if I think about sine, for example, its first derivative is cosine. I would have an omega. And its second derivative would be minus omega squared sine omega t. So I can match here these omegas, and I get that omega squared is equal to 1 over LC. And that's how I end up with this relationship. And that's why I have sines and cosines as the way my, in this case, Q changes. So that means that if Q looked like sine, I would look like omega cosine. Thanks.